This is section 3.1. Again, this is another review section. 3.1 and 3.2 are both review, but this section is introduction to radicals and simplifying radicals. I'll let you read through this front part, and I went ahead and filled out the notes for problems 1 through, or examples 1 through 6. What I really wanted to jump into are the properties of radicals. So when we look at we're talking about the product and quotient property to simplify radicals. So it says if the nth root of A and the nth root of B are both real numbers, then if we multiply those together, then we can take the nth root of A times B. So you just combine what's inside the radical. Okay, and what's inside the radical we call the radicand. Right? So you can combine them. And again, here it's the quotient, it does the same thing. So the nth root of A divided by the nth root of B is the nth root of A over B. So you can combine them. Now, similarly, if you have the product, the nth root of the product, then you can split these up. And if you have the nth root of a quotient, you can split those up. So this works both ways, okay? And there are many times where you're going to be doing that, flipping one way to the other. Okay, so here is what this looks like. It says when simplifying an nth root, you remove all the perfect nth powers from the radicand. Note the product and quotient properties of radicals also work in reverse. And this is what I was just telling you. So here we have the square root of 5 times the square root of 75. So if we combine them as the square root of 5 times 75, we get the square root of 225, which is a perfect square. So it simplifies much easier. Okay, now here, the square root of 144, that would be the square root of 4. Now, if you don't recognize that this is a perfect square to jump all the way to 12, then you would be looking for, you would break this apart and look for those perfect squares. And then once you find those perfect squares, then simplify them and then get your number. Okay. Now, when you have variables that have larger exponents inside than what the root is, this can get tricky. Okay, and I'll show you a trick. You can do how they do it here, but I'll show you another trick. Okay, so first, what we need to do is we need to clean up 75. Okay, so here's what we're going to do. Let's list our perfect squares. Okay, so just off to the side. Okay, so we have 1 is a perfect square, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 25, 36, 49, 7, 8, 64, 81, 100, 11 is 121, 144, let's see, 13 is 169, 14 is 196, and then 15 is 225. I'll stop there and I'll just put dot, dot, dot. Okay. So here's what we want to do. Here's something that I just saw somebody simplify radicals, and I think this is the way they did it was so much easier. I've never seen this before. So since these are all our perfect squares, we have the square root of 75. 75 is going to fall in between here. Okay. So what we want to do is we want to start dividing. I don't want to go down and divide because you can't divide 75 by 81, 75 by 100. Okay. So we're going to go up. So 75 is not divisible by 64. 75 is not divisible by 49. It's not divisible by 36. It is divisible by 25. So that would be the square root of 25 times the square root of 3. And this is just an easier way to find those perfect squares. So the square root of 25 just turns out to be 5, and then here's your square root of 3 that stays inside. So that's just 5 times the square root of 3. Okay, so let's do one more. Now these are perfect squares. Okay, the one in example 8 is a perfect cube. We could do the same thing there, but let's just do this. Let's do 124. The square root of 124. So 124 is going to fall right here. So 124 is not divisible by 121. It's not divisible by 100. It's not divisible by 81. And then you just keep dividing. It's not divisible by 64. It's not divisible by 49. It's not divisible by 36. It's not divisible by 25. It's not divisible by 16. It's not divisible by 9. Oh, wait, you know what? This isn't going to be divisible. Sorry, my fault. Let's change this. Let's take, how about we do, let's take the square root of 320. So let's see. So at 225, that was the square root of 15. So 16 times 16, that's 256. Because we're trying to find those 17 times 17, that's 289. Let me just get a larger list here real quick. 324. Okay, there it is. And then I'll put dot, dot, dot. Okay. So 320 is going to fall in between here. So now I want to start dividing by these numbers until I find the largest perfect square. Instead of having to do 1 and 320, 2 and whatever that is, 3 and whatever that is. Okay, so since we have our list of numbers, we're just going to take 320 divided by 289. No. 320 divided by 256. Nope. 320 divided by 225. Nope. 320 divided by 196. Nope. 320 divided by 169. Nope. 320 divided by 121. Nope. Did I skip one? I think I skipped 144. But that's not going to be divisible anyways. It's not divisible by 100. 320 divided by 81. Nope. 320 divided by 64. Yep, there it is. So this is going to turn out to be the square root of 64 times the square root of 5. So that just cleans up to be 8 root 5. Okay. All right. So now here we have 40. Okay. Well, we could do the same thing. 1 times 1 times 1 is 1. Then 8. 2 times 2 times 2 is 8. Then we get 27. 3 times 3 times 3. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. And so on. And so 40 is going to fall in there. All right. So if I take 40 and I divide it by, sorry, if I take 40 and divide it by 27, well, that's not it. 40 divided by 8, that's it. So this would end up being the third root of 8 times the third root of 5. So the cube root of 8 just simplifies to 2, and then there's the cube root of 5. Now, when you write your answer, you want to make sure that that cube root is part of that radical. You don't want to make it look like it's 23 times the square root of 5. Okay. All right. Now, when you have variables, remember that the power of our radical is a 2. So that means I'm looking for pairs. So if I were to rewrite this as x to the 4th times x, and then rewrite the y as y to the 16th times y, that's what that would give me. And then if I break all this up, which you don't have to do this, once you get a hang of this, you'll see what's going to happen. Okay, this is what we've got. Now, here's what we do. The square root of x to the 4th, so what times what is x to the 4th? Well, that would be an x squared. Then the square root of x has to stay behind. Okay, now what times what gives you y to the 16th? And that would be y to the 8th, because remember, you add your exponents. Okay, and then we have the square root of y. So now we pull out front the x squared y to the 8th, and then inside we're just left with the square root of xy. Okay, this is our answer. Now, here's the shortcut, and it's actually a rule. Okay, if your exponents are divisible by the root, in this case we have a square root, then you can simplify that real quick. And all you do is divide by the power of a root. So 4 divided by 2 is 2, so that's why an x squared came out. And the x has to stay inside. 16 divided by 2 is 8, and this y has to stay inside. Okay, so now that I've told you that, we can do this one real quick. 12 is divisible by 3. So 12 divided by 3 is 4, so that means we have a to the 4th. Now, 20 is not divisible. Actually, you know what? Let's do this. Okay, so here's the a to the 12th. Now, b, well, if I'm looking for multiples of 3, so 3, 6, 9, 12, 15, 18, that gets me close. The next one will be 21, and I overshot it. So this would be b to the 18th times b squared, and then here's your c. So 18 times 2 is 20. And the reason I did this is so I can see my exponents are the exponents that are divisible by 3. 12 divided by 3 is 4, so that's an a to the 4th that comes outside. 18 divided by 3 is 6, so b to the 6th comes outside. And then the rest has to stay inside. So the b squared c has to stay inside. Don't forget your cube root. Okay. All right. Now, number 11. We can take the cube root of a negative number, because a negative times a negative is a positive times a negative is a negative. All right, so that's okay to do. Now, if we look at just the short list that we had over here for our cubes, 24 is going to fall right here. Okay. All right. So So that's going to give me 24 is divisible by 8. So we'll have the cube root of -8 times 3. Now I need to rewrite the x to the 5th to where I have power divisible by 3. So that would just be x to the 3rd times x. And then y to the 9th. The 9 is divisible by 3, so we're good. Okay, so let me do it this way now. So the cube root of -8 is going to be -2. The cube root of x to the 3rd is just going to be x. And then the cube root of y to the 9th, 9 divided by 3, is going to be y to the 3rd. And then whatever you have left stays inside. So inside we have a 3 and an x, so the cube root of 3x. So minus 2x y to the 3rd times the cube root of 3x. Okay? All right, now number 12, we're back to square roots. All right, so let me erase this arrow. All these other things. Okay, so we have the 6 that's out front, and then I have the 24. So 24 is going to fall in here. Well, is 24 divisible by 6? Nope. Is 24 divisible by 9? Nope. Is 24 divisible by 4? Yes, it is. So here's 6. Inside, we're going to have the square root of 4 times 6. Now I need this is a square root, so the power of my root is a 2, so I need to change the x to the 5th. That would be an x to the 4th because I need it divisible by 2 times x, and this would be y to the 8th times y. Okay, so now, here we go. We're going to take out our perfect squares. Here's the 6 that's already on the outside. Okay, 4 is a perfect square, so that's going to come out as a 2. 4 divided by 2 is 2, so this is going to be an x squared. 8 divided by 2, that's going to be a y to the 4th. And then everything else I have to leave inside, which is a 6xy. So this is 12x squared y to the 4th times the square root of 6xy. Okay. Now number 14, we get into the radicals. And so for the radicals, you can always, these get kind of tricky because the way you simplify them, it just depends on what's going on. So here, I notice the denominator is a perfect square. Okay, so what I would probably do is go ahead and we're going to break this apart and say the square root of 18x cubed over the square root of 4y squared. Now, in the denominator, that's a perfect square, so that's just 2y. In the top, we need to break apart the 18. Well, 18 is going to fall right here. Well, is 18 divisible by 6? Nope. Is 18 divisible by 9? Yes, it is. So 18 divided by 9 is 2, so that's the square root of 9 times 2. And then I'm going to break the x to the 3rd apart as x squared times x. Okay, so now in the top, I'm going to take out my perfect squares. In the bottom, I have a 2y. So in the top, the 9 comes out as a 3. The x squared, 2 divided by 2 is just 1, so that's an x. And then we have the square root of 2x. And this is our answer. Now, I know it's tempting. You see those 2's, you want to reduce those, but you can't because one's in the one's in the radical, and the other one is not. Okay. All right. So 15 depends on how you want to break this apart. Let's see. If we, these are both divisible by 2, so that would be 5. Okay. So let's go ahead and combine these and into one radical. So 10a to the 4th over 32. Now, the reason why I did this is 10 and 32 I can divide by 2. So 2 goes into 10 5 times. Here's the a to the 4th. 2 goes into 32 16 times. Now I'm going to go ahead and break this apart. So I have the square root of 16 in the bottom. And then in the top, we have the square root of 5a to the 4th. Okay, well, the bottom, square root of 16, is just 4. A to the 4th, I can't do anything with the 5, but 4, the exponent of 4 divided by 2, that would be an a squared that comes outside, and the 5 has to stay inside. So that's how that simplifies. Okay, so this can be, it can be tricky, right? Okay, so now let's look at the next part. Okay, and I'll let you read the simplified form of a radical. So this is how you need to be leaving your answers. Okay, all right. All right. Now, when we add and subtract radicals, some people have a hard time with this, but this is nothing more than combining like terms. So when you have like terms, remember you have to have the same variable or variables and their exponents have to match. Well, for like radicals, the radicals have to be exactly the same. So when we look at this is the square root of 2x, and then I have another square root of 2x. So these radicals are the same, which means these are like terms. These are not like terms. This is the square root of 2x and then the cube root of 2x. So the power of the roots are different. Those are not the same. These are not the same because this just has the square root of x. This is the square root of 2x, and I can't take the 2 out because it's not a perfect square. So these are not radicals. Now, the way that they have you simplify this is the way the book tells you how to do it is they tell you to factor out the like term and then add their the coefficients or whatever's left. And to me, that just seems like it's a little bit overkill, and you can just look and combine the like terms as is. So for number 1, we have 2x plus 5x. Well, here are our like terms. They both have x's. So 2x plus 5x, we know that's going to be 7x. So for 1b, notice that both terms have the square root of 3. So that's 2 square root of 3 plus 5 square root of 3. You can think of it like, okay, I have 2 apples plus 5 apples. It's the same thing. So I have 7 apples. So it's just 7 times the square root of 3. Again, the radical is acting as the part that tells you it's a like term. Okay, so for 2a, 18a minus 19a, well, we know how to do that one. That's just minus a. Well, the same thing is going to happen over here. Notice that they both have the same term. It just happens to be the cube root of 9. And be careful, this doesn't mean 9 divided by 3 is 3, so this is going to turn into a 3. That's not what that means. Okay, So you have like terms. So you have 18 of these minus 19 of these. So it's negative cube root of 9. Okay? So don't make a big deal out of it. Just make sure that your radicals are the same. If they're the same, then add or subtract their coefficients. Okay, so here, number 3, I see the radicals. Root 2, this is a root 2, so that's great. My fractions already have common denominators, which is wonderful. So then I just combine what I've got. So 3 plus 2 is 5. So 5 over 5 times the square root of 2. 5 over 5 is just 1. So that just leaves us with the square root of 2. Okay. Then for number 4, here are your like terms. So basically, we're just doing 4 minus 2, which is 2. 2 minus 8, which is a minus 6 times the square root of 3. That's it. All right. Now, 5 is a little bit different because notice that we have the same terms there, and this one is different, and that's okay. This is like if we were to combine 2x, like 7x plus 3x minus 2y. Well, I can't combine the x with the y. I can only combine the x's together. So here, this is just going to give us 10 times the square root of 5 minus 2 times the square root of 2. Because the square root of 5 is not the same as the square root of 2. It's different. Okay? And then here, notice that you have, all of those have the square root of the fourth root of 7. All right, so, and then we have this minus 2 that's just going to hang on for the right. So 9 minus 4 is 5. 5 plus 30, that's 35 times the fourth root of 7 minus 2. That's it. That's all we had to do. Okay. Now, the next part is that we notice that these are not the same, right? So, but I notice that 27 can be broken down. Okay. So I have 5 square root 3 minus, well, 27 would be 9 times 3. So this is 5 root 3 minus the 9 comes outside as a 3, and then this other 3 stays inside. So now I have like terms. So 5 root 3 minus 3 root 3 is just 2 root 3. So we had to simplify our radicals first. Okay, so now number 8. This first term, the 4 is a perfect square, which is going to come outside as a 2, so this x has to stay inside. Plus 12 square root x, well that's nice because now I know I have like terms, minus the square root of x squared is just x. And that is not the same as these other two, because these other two have radicals, this one does not. So this is 20 root x plus 12 root x minus x. So that's 32 root x minus x. Okay. All right. Now, here we have the cube root. Well, the cube root of 8 is 2. So we have the cube root of x still left inside. Here's another 5 that's on the outside. The cube root of 125 is 5. And then I have another cube root of x. So this is 10 times the cube root of x plus 25 times the cube root of x, and that cleans up to 35 times the cube root of x. Okay. All right. So if you want to try the next ones by yourself, go ahead and pause the video. Okay. So I can't do anything with the square root of 2a. Now, the square root of 72a, I know 36 times 2 is 72. And then for the 8a, well, that would just be 4 times 2. Okay, so here's the square root of 2a. Here's the 4 that's out front. The 36 comes outside as a 6. And there's the square root of 2a. So again, like terms. And we have the 4 that's out front. And then the 4 inside comes out as a 2. And inside I have another 2a. So all three of these have the same radicals. So I'm going to clean up the numbers in front. Okay, so now this doesn't have a number in front, but how many root 2a's is that? That's just 1, right? So 1 minus 24 is negative 23, right? And negative 23 plus 8 is negative 15. So negative 15 times the square root of 2a. All right, so now we have these numbers that are getting bigger. Okay, so maybe we need to go back and look at our table. So, okay. So to the side. All right, so 150 is right here. And so I need to start dividing by all of those perfect squares. So 150 divided by 144, well, I know that's not going to happen. Okay. And then 150 divided by 121, no. 150 divided by 100, no. 150 divided by 81, no. Oops. 150 divided by 64. Nope. 150 divided by 30. Wait, where are we? 49. Nope. 150 divided by 36. Nope. 150 divided by 25. Yep, that's it. So this is going to be 25 times 6 times x squared times y square root plus 19 times, well, now 300 is a little bit easier to figure out. 300 is 3 times 100. And so the 100 is a perfect square. We have the x squared y. Okay, so now we're going to take out our perfect squares. So 25 comes out as a 5. The x squared comes out as x, and I'm left with a 6y. Plus, here's the 19. 100 comes out as 10, and the x squared comes out as x. And inside, we're left with a 3y. So 5x times the square root of 6y plus 190x times the square root of 3y. Now these, I'm so sorry, guys. So these are not like terms. This is the square root of 6y and the square root of 3y. There is nothing that I can do with this. So this is my final answer. That's as far as we can go for simplifying it. Okay. All right, so number 9. Here's the 9 that's on the outside. 45 would be 9 times 5. And then minus 9 times, and then 125 would be 25 times 5. Minus 8 times, and then 80. How would we break apart 80? My mind just went blank. Yeah, 16 and 5. Okay, so do you notice how all three of these have that 5 factor, and then the other factors are perfect squares? So this is going to be 9 times 3 times the square root of 5 minus 9 times 5 times the square root of 5 minus 8 times 4 times the square root of 5. So 27 root 5 minus 45 root 5 minus 32 root 5. So 27 minus 45 minus 32 gives us a minus 50. So minus 50 times the square root of 5. Okay. All right. Last problem. It's this little word problem. They want us to find the perimeter of this rectangle. Okay, so remember that your formula for the perimeter of a rectangle is twice the length plus twice the width. So my length is going to be the square root of 20, and the width is going to be 3 root 5. And, you know, since you're multiplying both of them by 2, it really doesn't matter which one you call the length and the width. It just wants the perimeter, right? So the square root of 20, well, that's going to be 4 times 5. And this is going to turn into 6 root 5. Okay, so when I bring this 2 out, I'm not going to show the step. I'm just going to do it. When I bring the 4 out, it's going to come out as a 2. So 2 times 2. So this is going to be 4 root 5 plus 6 root 5. And that's going to simplify to be 10 root 5. So the perimeter of this rectangle is 10 root 5. They didn't give us a unit, so we don't have to worry about writing a unit. All right, that's it.